All right, so on page 14, we're going to start talking about metric prefixes, which are just little letters we can add to the beginning of units that change what they mean. And we're only going to cover through example number 6 in this podcast. I do not need you to do 7 through 9 or any other problems at home on your own. Those are going to start to incorporate these metric prefixes into some more involved problems. So just get 1 through 6 done with any notes you need to around the top, and you'll be good for your stamp. So, metric prefixes. We talked about units already, and kind of base units and derived units. Well, when I'm talking about base units here, I'm talking about any units. They could even be derived units that have, but I'm talking about units that have no prefixes on them. That's what we consider a base unit in the context of metrics. So, they might not all be the SI base units. Any unit can get this kind of prefix put in front of it. And these prefixes just change the size, the kind of scale of that base unit. So you've probably heard of meters and kilometers. Well, that kilo prefix represents 1,000 meters. So it just makes it extra big to measure extra long distances. Meter is still our base unit. It's a standard international base unit for distance, but then we can also make it extra big or even extra small, like a centimeter, to measure kind of smaller things in science classes. So these prefixes just change the size of these units. And this table with these 4 prefixes are the 4 prefixes you need to start working on memorizing. And I know in this table I have all of these values, these numbers, in scientific notation. You don't have to memorize them in this form, but this is the form I'm giving you because it helps you see. We've already talked about scientific notation. These exponents being negative mean these are smaller than 1, meaning these prefixes make our unit smaller than the base unit. This positive exponent tells us that kilo and others are larger than the base unit. And so if you would rather think of these numbers in standard form, you can consider that 1,000. Like I said, there's 1,000 meters in 1 kilometer. You don't have to memorize that it's 10 to the third. I don't really care what form these numbers take. Either way, it's going to result in the same conversion and the same final answer. Now, how we use these numbers is going to be important, because just memorizing the number, you could get it backwards. You could start thinking there's 1,000 kilometers in 1 meter. So the way we intend you to use these numbers in the table is kind of in this, this is kind of a general formula for it. If you take the number from the table, like the kilo, for example, we can say that there's 10 to the third of whatever base unit we have here. So that could be like meters. In 1, and what's the prefix that goes with kilo? K, of the prefix symbol. So there's 10 to the third meters in 1 kilometer. Or like I said before, if you don't like scientific notation, then you can say there's 1,000 meters in 1 kilometer. But it's always putting the number with the base unit that doesn't have the prefix on it and setting that equal to 1 of the prefix unit, the prefix with that same base unit. So I have a couple examples down below. Did the exact same thing with kilo down here, just with grams. Doesn't matter what the unit is, this equation is still the same. That's why I put this generic U here, because any unit can get plugged in here. Seconds, grams, liters, meters, any of them. So we see that same kind of equation that I just wrote out for meters, telling us that there's 10 to the third grams in 1 kilogram. Or if we wanted to look at the centi prefix, there's 10 to the negative 2 meters in 1 centimeter. Now, you might be thinking, oh, from kindergarten or even middle school, you might have remembered that there's 100 centimeters in 1 meter. If that is already in your head, that's fine. That's just kind of changing around this to be a positive exponent and moving it over to the other side. They basically did some algebra with these equations that I've given you. You are responsible for knowing these 4 prefixes and how to do conversions with them, whether you use my numbers in my kind of formatted equations or your own numbers from your own head there. So we're going to look at a few different examples and practice writing conversion factors that could be used with each of these measurements below. So we're not doing any calculations yet. We're just practicing using this table to write the required equations. So to go from kilograms to grams. First, find your base unit. Find the part of those units that are the same on each side. And then whatever is different is your prefix. So we're going to be looking at our kilo prefix here. And 10 to the third is our number. And that's 10 to the third of our base unit equals 1 of the prefix unit. Even though this has the kg on one side and the g on the right side, it doesn't really matter. We could switch the order of these, but I'm just writing this in the same format as that general equation that I gave you earlier, starting with the number from the table. Now, if we look for what's the same in this next problem, m is the same on both sides. And notice how we have a k for kilo and an n here. So these are two different prefixes involved in this problem. And so when we work out this problem, if we were trying to do a conversion, a calculation here, we would need to use two different prefix equations to do two separate conversions. So let's go ahead and start with our kilo conversion like we've been doing. We're going to start with 10 to the 3 of our base unit, which is meters, equals 1 kilometer. A lot like what we just wrote up above. But then we're also going to need that nano conversion, and nano is 10 to the negative 9. And that 10 to the negative 9 is still going to go with the base unit equals 1 of the prefix unit. So these are two separate conversion factors, two separate unit equations that we could use to do our conversions. This next one, finding our base unit, the part that's the same between both, it's going to be liters. And once again, we see two different prefixes here. Our little m is milli, and then our c is centi. So we're going to have to write two different unit equations here. Our milli equation, if we start with that, is going to be 10 to the negative 3. Still putting that with our base unit, which is not meters this time, it's liters. And then that's equal to 1 of our milliliters. And then if we want to write our centi equation, centi is 10 to the negative 2 base units equals 1 of our centi, or prefix units. So those are the conversion factors. Those are the unit equations we can turn into conversion factors to do a conversion if we were asked to. If we were told to do like 37 milliliters into centiliters, we could plug those conversion factors in to our dimensional analysis to do that. So let's look at a couple of examples where we do actually use these conversion factors in calculations. So these probably look familiar. These are all, conversions that we've done and kind of touched on just a little bit, milli, nano, and kilo. So let's go through the first process again. Before we even start dimensional analysis, let's find what conversion factors we're going to need by looking at what unit is the same between both. Here our little m means we're dealing with milli, so we are going to need 10 to the negative 3 of our base unit equals 1 milli unit. So 10 to the negative 3 seconds equals 1 millisecond. And that's our conversion factor. Now we're going to use dimensional analysis with our given, which was 25 seconds. And when we're doing our dimensional analysis here, since I have seconds, plain old seconds on top, I'm going to start by putting the plain old seconds side of my equation down on bottom, following that diagonal rule. And then that means I can put my 1 millisecond up on top. And if in my calculator I do 25 times 1 and divided by 10 to the negative 3, remember we multiply numbers on top, we divide by numbers on bottom, and then we get 25,000 with 3 zeros there on the end, and that would of course be milliseconds there. So same process we've been using, we just have to use those metric prefixes to come up with a few new equations that we might not know off the top of our head. Let's do that again with this next example. Looking at our units to figure out what prefixes we need, find the part that's the same. That's going to be m for meters. The part that's different is going to be the equation that we need to write. Little n is nano. So that's 10 to the negative 9 of our base unit equals 1 of our nano base. So 10 to the negative 9th meters equals 1 nanometer. And if we take our given, which was 352 nanometers, then we're going to take the nanometers side of our equation this time and put that down on bottom because we had nanometers on top. We need those to match, which means we're going to be putting that 10 to the negative 9th meters on top. And now we can just multiply 352 times 10 raised to the negative 9th power. And there's a chance your calculator at home might struggle with this or show this in a different form, but I'm getting some scientific notation out because my calculator doesn't want to write all those zeros. So I got 3.52 times 10 to the negative 7th, and that would be meters, of course. Now in this last example, finding the units that are the same on both sides, that's going to be G for grams. Notice we have two different prefixes here, so we are going to need two different unit equations. This is going to be a two-step dimensional analysis. But let's go ahead and start with that nano. It's going to look a lot the same as the previous one, just with grams instead of meters. And then kilo is 10 to the third. So that's going to be 10 to the third grams equals 1 kilogram. So here we've got our two equations, and we still need to start with our given, which is this 5.30 times 10 to the 14th nanograms. So because nanograms is the unit that I've got to start with, we're going to start by putting the nanograms, which means 1 nanogram on bottom, 10 to the negative 9th grams goes on top. Just taking this first conversion factor and arranging it to follow that diagonal rule so that these cancel out. But this time we're not done because we don't have the kilograms that we want. So now we need to use our second equation. Because we have grams on top, we're going to take the gram side of this, that 10 to the third grams, put that on bottom, and then 1 kilogram goes on top. So just two sequential conversion factors to get from one prefix unit to the other. We're not going to or from the base unit. And this ends up turning out to be 530. I'm going to add a decimal point to keep that same 3 sig figs that we started with. And of course this would be kilograms because kilograms is what we had at the end. So hopefully this isn't too scary. Our conversion factors are the same as dimensional analysis. We use them the same way. It's just now you've got to remember a few prefixes, the most common ones, to use on your own for these conversion factors.